5.3 Fundamental Theorem of Calculus. And efficient integral calculations. All right, there are two versions to the fundamental theorem of calculus. We'll show both right now. And they're basically formulaic and form the central idea of all of calculus that we've discussed so far. So version 1, you might say, let's write fundamental theorem of calculus part 1, is the idea that the two operations of integration, that is the definite integral now, and derivative, those two operations are inverse procedures. So f of x is the same as d dx integral a to x of that exact same function, something like that. So basically it says, if I take the integral, the definite integral of some function from an arbitrary value a until a variable x, right, that'll produce a new function, right, an integrated function. It would be like an area function in a sense, right? I don't want to get too much into it. I just want you to be able to use the formulas properly and understand them a little bit without getting too deep into it. But right now, you can think about this function as being integrated across a certain interval from a to an unknown value, and that creates a new type of function. And if you differentiate that function, right, so first you've integrated f, and now you differentiate you differentiate the integrated function, you will get back to the original function f. So therefore the definite integral process and the derivative process completely undo each other and leave you back at f. Okay? So that's the main idea behind this expression here. Fundamental Theorem of Calculus Part 2, which is probably more important for the rest of the chapter than the Fundamental Theorem Part 1. And that is, if you're going to integrate over a defined interval a, b, some function f, so what are you really finding? You're finding the net area between this function and the x-axis, we discussed that before, across a certain interval, right? This is an area. Then a way to evaluate that without having to resort to the limiting process that we discussed before, to avoid that, is you can simply take cap f at the latter location and subtract off cap f at the former location, and that will be the same as this area. So this difference of f of b minus f of a, this difference will be the same as this integral, as long as cap f is an antiderivative of little f. So no longer do we need any type of limiting process or complicated Riemann sums or anything of this nature. We can simply take the antiderivative, I say the antiderivative, it's really an antiderivative, I'm going to say the antiderivative of f. I can plug in the two values, a and b, and subtract, and I'll get the same thing. So let's take a small example. We went through a very complicated process before when we wanted to figure out the area under x squared from 0 to 2. We got the answer as 8/3 using Riemann sums and a limiting process in section, I think, 5.2, if I'm not mistaken. We found it was 8/3. we first found an overestimate using Riemann sums and an underestimate using Riemann sums with only 4 rectangles or something like that. And then we used a limiting process on a Riemann sum to get down to the exact value of 8/3. We were convinced it was the case. So instead of doing all that, what we're now revealing through the fundamental theorem of calculus part 2 is that that is not necessary to perform in all these cases. Rather, you can take an antiderivative and subtract. So although we found this through a limit of Riemann sums, there is a secondary, more important and efficient way to do this, and that is the antiderivative of x squared is, we know from the reverse power rule, 1/3 x cubed. And I want to evaluate that. It's a common way to write this initial move here. Find the antiderivative and then place the limits of integration along this bar, 0 to 2, okay? As a segue to actually doing this calculation of f of b minus f of a. So here's capital F, we just found, right? There's capital F of x, which is an antiderivative of x squared, the simplest one. I don't put plus c here, right? I choose c to be 0, so it's the simplest antiderivative of x squared, you might say. And now what I want to do is plug in 2 and 0. So I'm going to put in 1/3 2 cubed minus 1/3 0 cubed. Okay. So there is f of b minus f of a, right? Just like we expressed here, it's the antiderivative with the 2 limits of integration plugged in, right? Latter minus former, and then we just evaluate. Well, this is totally gone because it has a 0 in there, and now we just have 2 cubed is 8 on 3. We get 8/3, just like we knew when we performed the limit of the Riemann sums and got the same result in a slightly more complicated manner. Okay, so this rule, the second part of the fundamental theorem of calculus, is going to greatly eliminate all those more difficult procedures that we might have had to perform just with the simple use of antiderivatives.